Batch fermentation is the process of growing cells under controlled conditions using a one-pot media formulation, as opposed to fed batch, where a starting media is fed over time. Fermentation is advantageous over shake flask cultivation because of the ability to control culture parameters, including temperature, pH, and oxygen level. The advantage of this system is that it is simple, little experience is required to set up, and limited input required, especially when auto-inducing media is used. The disadvantage with respect to fed batch is that there is little control over cell growth and there's low relative productivity, usually due to the production of byproducts, including acid, which lowers pH, causing early entry into cell death. As mentioned in an earlier video, cell division is exponential, assuming unlimited nutrients. Eventually, cell number or nutrients become a factor, causing a slowdown in growth. To better understand the growth characteristics in culture, doubling time can be calculated according to the formula shown, where the initial cells increase by the factor e to the mu t, where mu is the specific growth rate and t is time. The doubling time can be calculated if mu is known using the formula doubling time equals the natural log of 2 divided by mu. Doubling times for bacteria are greater than fungi, and mammalian cells have the slowest doubling time as shown by the table. Growth rates up to 2.1 per hour are achievable with bacteria, but practically fermentations are run at a slower rate as inclusion bodies can form if cells grow too fast. Anabolic processes are those involving creation of the building blocks of cells. A general rule is that 100 millimoles of ATP is needed to generate 1 gram of cells. The energy required to create the cells is then based on the amount of ATP generated per growth substrate. For glucose, 1 millimole generates 28 millimoles of ATP, so 4 millimoles of glucose, or about 0.8 grams of glucose, is needed to generate the energy to build 1 gram of cells, and along with 1 gram of glucose for the material for cellular components equals a total of 1.8 grams of glucose to generate 1 gram of cells. Therefore, the cellular yield, or Y, is gram cell per gram glucose, or 1 over 1.8, which equals 0.55. In practice, though, the amount is closer to 0.45. If cells are grown in rich media, then less energy and materials are required to create 1 gram of cells, since the preformed building blocks come directly from the media. In this case, the yield is 1.1 gram cells per gram glucose. Growth under anaerobic conditions is a different story. Because glycolysis is the only source of ATP, less energy is produced per gram of glucose, and only 2 millimoles per gram glucose in fact. If 100 millimoles of ATP is needed to make 1 gram of cells, then 50 millimoles of glucose, or about 9 grams, is needed to generate the energy to build 1 gram of cells. Add to that the 1 gram for cellular components, and that equals 10 grams of glucose per gram of cells, so the yield is 0.1 gram cells per gram glucose. We will assume the culture is grown aerobically for the remainder of this presentation, as this is the most common way to grow cells. Under batch conditions, cells will grow at mu max until cells enter stationary phase. This occurs because either nutrients run out or oxygen becomes limiting, forcing cells to die if they are strict aerobes, or into anaerobic growth for facultative anaerobes like E. coli. In this case, cells start to generate acid and other waste products which slow growth. Other parameters that affect growth include temperature, pH, and pressure, as well as aeration and agitation, which are linked, and foam. Foaming is the process when fermentation byproducts or dead cellular material reacts with air, creating bubbles which carry out of the vessel. We will discuss strategies to manage foam later in the lecture. Growth rate increases with temperature until the temperature limit of organisms. At this point, cellular machinery degrades, leading to cell death. Temperatures can increase by heating the system or through exothermic processes in the cell that generate extra heat, as is observed in steaming mulch piles. As mentioned before, temperature has an effect on protein expression. Growth at max temperature puts a strain on cells, which can result in inclusion body or denature proteins. For this reason, many fermentations are run at lower temperatures to achieve slower growth rates, resulting in higher product yields. Common strategies include growing cells at optimal growth temperature, then lowering the temperature to between 10 to 30 degrees Celsius after inducing expression. In some cases, it is advantageous to increase the temperature, such as in the case of plasmid production, or if expression is under the control of a heat shock promoter. Organisms typically operate under a pH curve where too high or too low pH can cause growth rates to slow or cell death. In addition, some media components are pH sensitive and can precipitate at the wrong pH. Cells self-regulate intracellular pH, so proteins produced inside cells are not affected by changes in the pH of the media. However, secreted proteins are. For example, Pichia typically grows at pH 5. In addition, pH can also affect protease activity, which can impact cellular yield. Increasing pressure, which is only done in stainless steel systems, can be used to increase dissolved oxygen concentration. This strategy isn't used often in smaller systems, but employed in larger systems when head pressure becomes an issue and may impact cells at the bottom of the tank. Aeration is a strategy used to introduce oxygen into tanks. As well as mixing, aeration also removes other gases and volatile compounds from the culture. Bubble size is related to gas transfer, with bigger bubbles being less efficient in O2 transfer. Aeration is measured as vessel volumes per minute, or VVM, which is simply the amount of airflow relative to the size of the vessel the culture is in. Too much aeration can lead to foaming and other problems. Agitation is also used to increase oxygen in cultures and used for mixing, especially in smaller vessels. Impellers are part of the agitation system, and there are a wide range of impellers available, with the Rushton style the most common for microbial cells. Different impeller types can be combined. In large tanks and cell culture, shear stress can be a problem, so other impellers may be implemented. Foaming can be a major problem in fermentation. It is caused by protein-rich media, high stirring or aeration rates, and/or metabolic products. It is typically controlled using a chemical antifoam, but can also be controlled mechanically and lesser so by ultrasonication. Antifoams such as PPG 2000 work to break up foam, but can be used by microbes or cause decrease in growth. Most are silicone-based chemicals. They can cause coalescence of bubbles and can affect sensors that measure oxygen. Antifoam is usually added before fermentation. In combination with antifoam are foam level probes. As we'll see in future lectures, there is a feedback loop where foam is detected by the level probe. It actuates a pump that then adds antifoam. The pump stops when the level or foam decreases, but can be problematic if the level probe is too sensitive. This problem is ameliorated by having a small amount of antifoam or short duty cycles when the pump is activated. This problem is more pronounced in fed batch culture, which we will be learning about in our next lecture.